Hello students, today we are going to discuss the first topic of class 10 mathematics book, that is real numbers. In real numbers we will discuss Euclid's division lemma, Euclid's division algorithm, fundamental theorem of arithmetic, the rational numbers, and finally rational numbers. So first let us discuss Euclid's division lemma. To understand Euclid's division lemma, let us take the following pair of integers 4, 20, 5, 17, 6, 19. If we divide 20 by 4, then quotient is 5. So it can be written as 4 into 5 and remainder is 0. So this is our quotient, this is our remainder. This is our quotient, this is our remainder, this is our divisor, and this is our dividend. Similarly, if we discuss divide 17 by 5, then we get 5 into 3 plus 2. Here 3 is the quotient, 2 is the remainder, and if we divide 19 by 6, then 6 into 3 plus 1. So 1 is the remainder. So Euclid's division lemma says, so the theorem says, the lemma says, lemma theorem says, given two positive integers a and b, there exist integers, unique integers q and r such that a equal to bq plus r, where zero is less than equal to r is less than b. So this is the Euclid's division lemma. This is Euclid's division lemma. So this, using Euclid's division lemma, we will find ACF of two numbers also. How to find that ACF of two numbers? Suppose let us try to find out ACF of 15 and 12. So we write like this: 15 is equal to 12 into 1 plus 3. 12 into 1 plus 3, so 1 is the quotient and 3 is the remainder. Again this 12 can be written as 3, this remainder 3 into 4 plus 0. So when this remainder becomes 0, the last remainder is the ACF of these two given numbers. So here ACF equal to 3. ACF is equal to 3. So this is called Euclid's, this steps of finding the ACF of two number is called Euclid's division algorithm. So Euclid's division algorithm is basically steps for finding ACF of two numbers. So Euclid's division algorithm. What it says? So let C and D be two positive integers C is greater than D, C is greater than D, say, then for finding ACF, the step 1, apply Euclid's division lemma on C and D. So C is equal to, we can write dq plus r, where r is greater than equal to 0, r is greater than equal to 0, and it is less than d. The second step, if r is not equal to 0, again apply the lemma on D and R, and continue the process until R becomes 0. So this is what the Euclid's division lemma, and when R becomes 0, the last remainder is the ACF of the two numbers that is C and D. Next, we'll try to find out ACF of two numbers with the help of Euclid's division algorithm, say 120 and 25, something like this. So let us try to find the ACF of 120 and 25. So how to find it out? We can write by Euclid's division algorithm rhythm 120 is equal to 25 into 4 plus 20. Next, we again apply this division algorithm on 25 and 20. So you can write 25 is equal to 20 into 1 plus 5. So remainder is still not 0. So again we will apply the division lemma on 20 and 5. So 20 is equal to 5 into 4 plus 0. So now the remainder has become 0. Last, this is remainder is our required ACF. So ACF of 120 comma 25 is equal to 5. So this is the way of finding the ACF of two numbers by Euclid's division algorithm. Now, one interesting question can be solved with the help of Euclid's division lemma. So let us, square of any integer is of the form is of the form 3m or 3m plus 1. So this is a textbook question. How to prove this one? So this question, square of any integer is of the form 3m or 3m plus 1. So using Euclid's division lemma, we can prove this statement. So how to do this? Let start like this. Let A be any positive integer and b equal to 3. B is equal to 3. A is unknown. A is an integer, and there are two numbers in Euclid's division number, A and B. Suppose A is the any positive integer and B is equal to 3. Then by Euclid's division lemma, A equal to BQ plus R. That means A is equal to BQ. B is 3, so 3Q plus R, and R lies between. R is greater than equal to 0. R is greater than equal to 0 and less than B. B is here 3, less than 3, greater than equal to 0. So therefore we can say that is R equal to what? R is equal to 0. R can be equal to 0. R can be equal to 1 or 2 at most. So these three cases arises. Any positive numbers can be written as 3q plus 0, that is 3q plus 3q, or 3q plus 1, or 3q plus 2. Any positive integer can be written as 3q, 3q plus 1, or 3q plus 2. If we write b is 4, then a can be written as 4q, 4q plus 1, 4q plus 2, 4q plus 3, and so on. So here, since b is equal to 3, so a can be written as 3q plus 1, 3q plus 2, and 3q. So if If A equal to 3q, suppose A is equal to 3q, then A square is equal to 3q whole square, which is equal to 9q square, which we can write it as 3 into 3q square. So it is of the form 3m equal to 3m, where m equal to what? 3q square. So in this place, we can, if we write m in place of 3q square, if we write m, then this s square is equal to 3m. Now second case, if A equal to 3q plus 1. If A is equal to 3q plus 1, then squaring both sides. S square is equal to 3q plus 1 whole square. S square is equal to 3q plus 1 whole square. So let us expand 3q plus 1 whole square. So 3q plus 1 whole square is equal to 9q square plus 6q plus 1. So this can be written as, if we take common 3, then it becomes 3q square. If we take 3 common from here, then we get 2q, but here we cannot take common, so it becomes remainder. So this is equal to, we can write this is equal to what? 3m plus 1. This is also of the form 3m plus 1, where m is equal to what? M is equal to 3q square plus 2q. If we write m in this place, if we write m in this place, that is 3q square plus 2q, in place of 3q square plus 2q, if we write m, then this s square is equal to 3m plus 1. So we write where m is equal to 3q square plus 2q. So two cases we have discussed. A can be 3q plus 1, also 3q plus 2. So if A is equal to 3q, then S square is equal to 9q square, which is of the form 3m. If A is equal to 3q plus 1 whole square, then S square is equal to 3q plus 1 whole square, which is ultimately equal to 9q square plus 6q plus 1, and it is also of the form 3m plus 1. Finally, last one, if A is equal to if A is equal to 3q plus 2, if A is equal to 3q plus 2, since R has taken 0, R has taken 1, R has taken value 2. So if R is equal to 2, then A is equal to 3q plus 2. So when A is equal to 3q plus 2, then squaring both sides, S square is equal to 3q plus 2 whole square, 3q plus 2 whole square. So expanding, 9q square plus 2 into 3, 6 into 2, 12q plus 4. So this can be written as 9q square plus 12q plus 4 can be written as 3 plus 1. We'll take out multiple of 3 from this. So it is equal to 3 plus 1. Now we take common 3 from here. Then we get 3 3q square plus 4q plus 1, and this one is outside. So what do you see? This is again of the form 3m plus 1 equal to 3m plus 1. 3m plus 1. This is again of the form 3m plus 1. Here m is equal to, where m is equal to 3q square plus 4q plus 1. So in all the three cases, we see that the square of the number is either of the form 3m or 3m plus 1. So hence it is true. So thus square of any integer positive of the form 3m or 3m plus 1. Hence